Hello, everyone. Let's do a little chemistry. We're going to take a look at calculations for chemical reactions. That's scientists, they love putting a word on every new idea. So to do calculations about chemical reactions, that's called stoichiometry. What a crazy word that is. Stoichiometry just means, hey, we got a chemical reaction, and usually it's represented by the number of moles you have. So many moles, so many, a quantity of reactants makes a quantity of products, how many moles there are. And you can then convert moles to particles with Avogadro's number. More commonly, though, you convert moles to grams because we can't see individual atoms or molecules. It's very difficult to count them out. Instead, you weigh them. And from using something called the molar mass, you can actually figure out how many particles are there, how many molecules are there rather, based on their weight, on the grams. You can also look at the number of moles of a gas, and this neat, interesting conversion factor, 22.4 liters at atmospheric pressure holds 1 mole, Avogadro's number of gas molecules. Anyways, the little diagram there, we'll come back to that when we need it. Today we're going to focus on the top right side here. We're going to be looking at molar mass, converting between grams and moles, doing a little stoichiometry. Fancy talk for calculations involving chemical reactions. Okay, key idea here is remember that 1 mole is this cool number called Avogadro's number, 6.022 times 10 to the 23rd. Think about using the word mole, this fancy number, just like you would use the word dozen, right? So if you have a dozen eggs, you have 12 eggs. If you have a mole of eggs, well, that's a lot more. It's 6.022 times 10 to the 23rd, heck of a lot of eggs. But we're not always going to have exactly 1 mole. We're going to have different amounts, different numbers of moles. So if I say we have 2.5 dozen eggs, you might have to think about how many eggs that really is, or you can use dimensional analysis to figure it out. How many eggs do we have? Well, we're given 2.5 dozen, and the conversion factor is 1 dozen has 12 eggs in it. Well, it has 12 something in it. Doesn't have to be eggs, could be donuts. And then what you do is the donuts cancel out, donuts. Dozens cancel out, and you multiply 12 times 2.5, and that should be 30 eggs. We're going to do the same thing with moles. Instead of using the word dozen, we're going to say moles. So hey, what if we have 2.5 moles of a reactant? How many actual molecules do we have? Well, we need another conversion factor, one that changes moles into molecules. And that's Avogadro's number, 6.022 times 10 to the 23rd. Cancel out the moles. Every 1 mole has Avogadro's number in it. And that by watching how the units cancel out, that helps me remember whether I'm multiplying or dividing by my conversion factors. Multiply this out, and it's a big old number. I'm going to do it somewhere in my scratch paper here. It's 1.5055 times 10 to the 24th molecules. That's a lot. I guess I wasn't too careful about my sig figs though, was I? There's 2 significant figures here, 4 here. So the calculator spit out this number, but to 2 sig figs, I shouldn't say this, I should say 1.5 times 10 to the 24th molecules. Cool. Okay, so we're going to get comfortable, I hope, the more we practice using the word mole. Just represents molecules. And guess what? We're not going to be multiplying out by Avogadro's number very often. I mean, there'll be a homework problem or 2, maybe 1 exam question says, hey, I like to know the exact number of molecules. But most of the time, it's just more convenient to talk about groups of moles, moles of this, moles of that. Cool. All righty. Hey, so we're going to do some calculations involving chemical reactions. So I just arbitrarily picked one. And hello, little pun there, HI, hi. That's hydroiodic acid. So why don't we make some hydroiodic acid? That'll be our chemical reaction. So I want to make some HI. It's a gas, but you know what? Let's just leave out the physical states here. And well, how do we make it? Or in other words, what's the recipe, right? If you're going to bake some cookies, make some cupcakes, you go look up a recipe on the internet or wherever, Pinterest, find the recipe on how to do this. And you need a certain number of ingredients to make the right cookies that taste good, right? On the right quantities of each ingredient. Don't leave out an ingredient, otherwise you make bad cookies. Same thing here. The chemical reaction, the balance chemical reaction, is your recipe for making products. So I wouldn't expect you to do this from scratch, but I'm just showing how general this is, right? So if we want to make this molecule HI, well, one way to make it is just from the elements. Let's go get some hydrogen and get some iodide. And guess what? This is not a good recipe. On paper or on the computer screen, it looks legit. But if you were to go to the grocery store for elements, you know, go to a chemical supply warehouse and buy some hydrogen atoms, they're sold prepackaged as hydrogen gas. Or in other words, hydrogen atoms don't exist all by themselves. They're too reactive. They pair up naturally. Same is true with iodide. And that's very common for the nonmetals. They typically pair up and form diatomic molecules. Okay. Again, I'm not expecting you to do this. You know, this is not an exam question. Let's make some hydrogen iodide. Oh, sorry. Well, hydroiodic acid. No, I'm just saying, well, how would you do it? This is how you do it. Go to the periodic table, grab the elements in their natural state. H2 is the natural form of hydrogen. Iodine, I2, natural form there. And hey, hydroiodic acid is 1H and 1I. So now we have the reactants, we have the products, but not the right quantities, right? This is not a balanced equation. Okay, so let's balance it. Two things to remember. Do not change the subscripts. Can't change the twos here. That changes the recipe, changes the balance equation. And then save the simplest molecule for last. Well, these molecules are already pretty simple. This one has two elements. The others only have one type of element. So these are simpler. I don't know, so maybe save the hydrogen for last, which means balance iodide first. So there's two iodine atoms on the left side. There's only one on the right, so put a big 2 in front. Now there's two iodines on both sides. And guess what? Hydrogen's already balanced, right? 2 H's on the right, 2 on the left. Nice. There's a good recipe. That's the balanced chemical equation for making hydroiodic acid. All right, now let's do some calculations. Suppose we want to make, well, this is where I would actually write an exam question and give you a quantity. But let's start out with basic principles. Let's start simple, in other words. So look at the recipe, and what is this saying? This says, one way to interpret this is go get one molecule of hydrogen, you know, 2 atoms of H stuck together, just one of them. Go get one molecule of I2, throw a spark in it, heat it up, mix them up, make them collide, do the chemical reaction, and hey, after some amount of time, you'll have 2 molecules of HI. 1 molecule plus 1 molecule gives you 2. You could also say, how about if we take a dozen hydrogen atoms and a dozen iodide atoms, a dozen of each, and you'll get 2 dozen HIs. More oftentimes, though, it's very difficult to actually count out 12 molecules in the lab, right? We don't have little molecular tweezers and grab these super tiny things we can't see. Now, let's get a huge quantity because they're so small. Something we can actually weigh in the lab, a reasonable amount. How about a mole? So if we take 1 mole of hydrogen and we add 1 mole of iodide, I2, we're going to get 2 moles of HI, hydroiodic acid. There's an invisible 1 here, an invisible 1 there. Typically, the units, if you will, for a balanced chemical equation are in moles. Cool. Nice. So I say, let's go and make 2 moles of HI. Let's just start simple. Okay, I want to get 2 moles of this. Here's my recipe. How many grams? Whoa, there's a little curveball. How many grams of each reagent do we need? Well, the number of moles is pretty easy. The balanced equation, the recipe, says you need 1 mole of hydrogen and 1 mole of iodine, I2. But the question says, well, how many grams is that? And that's a real problem. That's not the right way to say it. In reality, if you want to make 2 moles of HI, again, we don't have a way of counting out Avogadro's number of hydrogen gas by hand. What we have to do is weigh it. We will weigh it out, and from that, calculate how many molecules are actually there. And here's the tie-in. Avogadro's number is special because 6.022 times 10 to the 23rd, Avogadro's number of atoms will actually weigh the atomic mass in grams. So what are we talking about? Go back over here to the periodic table. Here's the atomic mass, sometimes called the atomic weight. For hydrogen, that number at the bottom, if it's too small of a font size, is 1.0079. It's the atomic mass unit on the average weight of a hydrogen atom. But if you have Avogadro's number of hydrogen atoms, then they will weigh 1.0079 grams. That's why Avogadro's number is special and very useful. And if you say Avogadro's number, it's the same as saying 1 mole, right? They're synonymous. 1 dozen equals 12. 1 mole equals 6.022 times 10 to the 23rd. Okay, so that's the cool part. And that actually allows us to answer this question. How many grams of each reagent do we need? Well, I want 1 mole. And 1 mole of H atoms, 1 mole of atoms, I'm going to choose hydrogen atoms, will weigh the atomic mass in grams. And the atomic mass of hydrogen is 1.0079. grams. So 1 mole of H2, right? That's what I want, hydrogen gas. Well, how many total hydrogen atoms are there? Well, every molecule has 2. There's 1 mole of the molecules, so just multiply the atomic number, I'm sorry, atomic mass, the atomic weight by 2 moles. And that's going to equal the number of grams of 1 mole of hydrogen gas. And that number is, where did I put it? 2.0158 grams per mole. So for every mole of hydrogen gas, it's going to take 2.0158. So that's really cool. Hydrogen is a gas, so you have to fill up a balloon. First, weigh the balloon first on the balance. Figure out the weight of the balloon. Fill up the empty balloon to some size, put it back on the balance, see how much more it weighs. Keep doing that. Got a little problem with hydrogen being lighter than air. It's going to float. So this will be very difficult in the lab. But the idea is, in a vacuum, you weigh out the hydrogen gas until it weighs 2.0158 grams, and that will automatically contain Avogadro's number of hydrogen molecules, 1 mole of H2. We also need 1 mole of I2 and iodine. Let's go look up on the periodic table. How many grams per mole is it? It's 126. Again, pretty small font size down there, but that number is 126.9045. 126.9045 grams per mole. That's the molar mass or atomic mass. So 1 mole of I2 is going to weigh, 1 mole weighs 2 times the weight of 1 iodide atom, 126.9045 grams. Multiply that together, and that's 253.8090. Wow, pretty heavy. Now, the question didn't ask for it, but we could ask, what's the mass of 1 mole of HI molecules? And that molar mass is just where you add up all the atomic masses. So 1 mole of hydroiodic acid weighs, well, the weight of hydrogen, which is right up here, 1.0079. And 1 iodide weighs right here, 126.9045. Add them together, and it's 127.9124 grams per mole. Well, that's the molar mass, the mass of 1 mole. Yeah, good name for it. Okay. Oh, let's just do the problem. Did we already do it? We did it. I missed it. So busy explaining molar mass. What was the question? Yeah, go back to the basics. How many grams of each reagent do we need? Well, you need 1 mole of each of those, and we just weighed it. We just calculated the weights, rather. So 1 mole of hydrogen, you need 2.0158 grams. For 1 mole of I2, you need 253.8090 grams. So to summarize here, suppose we want to make 2 moles. We just figured it out. You need 2.0158 grams of hydrogen, and you need 253.8090 grams of iodide. This 2 grams contains 1 mole of hydrogen gas, and 253, that's a huge number, is also 1 mole, but of I2. Why such a big difference? Well, I got little pictures of the atom. They're not drawn to scale. Hydrogen is much, much smaller than this picture. It's not the same size iodide. It only has 1 proton, 1 electron. But this is a good image for giving you an impression of how different in weight and in mass these atoms are. There's 53 protons, and 1 isotope of iodine has 74 neutrons. And remember, a neutron weighs about the same as a proton. So it's a huge weight, 127. Yeah, if you add up 53 and 20 and 74, that's a lot. Every atom weighs 127, whereas hydrogen only weighs 1. And so if you have 6.022 times 10 to the 23rd atoms of iodide, each one, iodine weighs 127, that's going to add up a lot of weight. Whereas Avogadro's number of a single atom of mass unit 1 here, that's not going to weigh very much, only 2. Cool. All righty, let's see what else we got. Back to the top, slide over. Kind of review or get some more ideas about what this recipe, this balanced chemical equation can do for us. Suppose you don't want 2 moles of HI. Instead, you go to the lab and say, hey, I got this leftover iodine. There's 2 moles of it here. Let's use it all up. And let's make some hydroiodic acid. So if I got this beaker with 8 moles of I2 in it, how many moles of hydrogen do I need? Well, look at the recipe, right? It says that 1 iodide requires 1 hydrogen gas. I should be saying I2 and one I2 molecule needs one H2 molecule. So I'm just pretty straightforward. If you have 8 of these, you need 8 of those. And you're going to make 2 times 8, which was 16. You basically just scale up your recipe. If the numbers are a little funny, like there are occasions when you see a crazy Balanced equation, a whole bunch of molecules, maybe there's a coefficient not of a nice whole number like 8, but maybe it's like 5 halves or something crazy like that. If things get a little weird, use dimensional analysis. So let's resolve this problem using dimensional analysis. And the way we have a video about that, the way I teach is I say, okay, first decide what you want. What do you want? What are you trying to solve? And it's right up here. The question says, you want to know how many moles. So write those units. We want moles of hydrogen gas. Put a little equal sign and a line here for to show your work. Step 1, what do you want? Moles of hydrogen. That's what the question asks for. And then scan the problem for any digits, any numbers. Here it is. There's a number 8 here. This is what we're given. So what are we given? What do we know? We know that there are 8 moles of iodide. Okay, that's step 2. Step 3 is find some conversion factors to change these units to those units. Well, it's a match already, right? We got moles here and moles there. The units already match, don't they? Well, when you do these calculations with chemical equations, you really have 2 units. This 8, yeah, has the units of moles, but this 8 is also talking about iodide, I2. But in the product side, on the answer side over here, we have moles, but of hydrogen gas, H2. So you kind of have to convert the I2 to H2. You kind of have to convert the molecules. And you use a recipe to do it. That's supposed to be a bracket. So what does that mean? We need to cancel out the moles of I2 and change them into moles of H2. And I messed up my chemical equation there. I messed up my recipe, so let's rewrite it. The recipe says that's a 1-to-1 ratio. 1 H2 requires 1 I2. So whatever numbers in front of your molecules in the balanced equation, those are your conversion factors. The recipe says one of these, 1 mole of I2, needs to react with one of these, 1 mole of H2. Cancel out your units, moles of I2 cancel out, and simply 8 times 1 divided by 1 is 8. I know, that was pretty straightforward, but I wanted you to see the method. Let's try it again down here. How many moles of HI can be obtained from 8 moles of I2? Well, one way is to reason it out. The chemical equation, the recipe says, well, if you have 1 of these I2s, you get 2, twice as many HIs. So if you start with 8 of I2, you should get twice as many, or 16. So you can just, if this question shows up on the exam, you can write 16 moles of HI. Isn't that weird? You can abbreviate moles, MOL. Yeah, why do we drop the E? I don't know. That'd be fine on the exam. I'll give you full credit. Now, if you mess up the algebra or the math here, and this is all you write in your test, then there's no partial credit. So I would suggest, if you're not 100% sure on your math skills or you mistyped something in the calculator, show a little bit of work. So you might say, okay, let's use dimensional analysis. What do we want? Well, moles of I2. So write it over here. Moles of HI, rather. Read the question, Dennis. Moles of HI. How many moles? That's what we want. Draw a line for some conversion factors. Look for a digit. Here's the number 8. What are the units? It's moles, but it's also I2. And again, step 3, find conversion factors. The moles can't match. We got moles on both sides. That looks good. The molecules don't match. So we need to change the molecule I2 to the molecules of HI. And anytime you're going to change molecules, you're going to use the balance equation. Can I abbreviate that? BAL EQN, balance equation. And it's right up here. Balanced equation, the recipe says, well, take 1 I2, 1 mole of I2, and you can produce 2 moles of HI. So whatever number's in front of the molecule in your balance, make sure it's balanced, doesn't work otherwise, balanced equation, those are your conversion factors. And so the moles of I2 cancel out. 2 times, sorry, that's 8 times 2 is 16, divide by 1, yeah, it's 16. Cool. And if you mess up and miswrite a 15 here, I don't know what might happen, some silly math error. At least I can look back here and say, oh, I know what you're doing. I can give you most of the points. Take off 1 point or a half a point for a bad math mistake. Okay, let's look at this one now. This question says, how many grams of hydrogen are required to produce 12 moles of HI? Okay, now you need to start showing some work. You still got the balanced equation. It's at the top of the screen, but let's rewrite it. 2, sorry, HI, balanced equation. Now it's asking for the weight. We can solve this a little bit in our head. If we want 12 moles of HI, we need half as much hydrogen, right? 1 mole of H2 gas produces 2 moles of HI. So if you had 6 moles of H2, that would produce 12 moles of HI. So we need 6 moles of H2. And then we have to figure out how many grams that is. Okay, we need to show some work. And I don't want, if I make a mistake, if I'm the student and I made a mistake, I want the teacher to see my thought process and give me some partial credit. So this one, I really recommend using dimensional analysis. Okay, so what do you want? We want grams of H2. So put it over here, grams of H2. It's what we want to find. Got the big line over here. Look for some digits. Oh, there's a 12. Start off with a 12. What are the units? Moles of HI. Okay. Now this is going to take a little more work. We have moles on the left, and we have grams on the right. And we have HI on the left, and we have H2 on the right. So we need to do 2 conversions. We need to change the moles to grams and HI to H2. And the way I think about it is anytime you want to change molecules, use the balance equation. But this balance equation has units of moles. Yeah. So we need 1 mole of H2, 1 mole of I2 to make 2 moles of HI. Oh wait, I have moles of HI. So let's get out of moles of HI and change them into moles of H. Okay, that we can do. Cancel out moles of HI and figure out how many moles of H2, because that's what we want. That's a real long 2 there. We can fix that. So the balance equation has the recipe tells us the ratio. If you want to make 2 moles of HI, 2 moles of HI, you're going to need 1 mole of hydrogen gas. Cool. And that, the use of the balanced equation helps us change the hydrogen iodide, HI, hydroiodic acid, into hydrogen gas. And now H2 matches H2. Good. We're getting closer to the answer. One more step though. We need to cancel out the moles and change them into grams. We need a conversion factor that has units of G over MOL. And did I put it over here? Well, we talked about molar mass. There it is. So here's the molar mass of hydrogen gas. Go to the periodic table. Periodic table says if you have 1 mole of hydrogen, it's 1.0079 grams. Then we did the math. There's 2 of them, 2 hydrogen atoms in 1 molecule. So if you have 1 mole of hydrogen gas, 2 times the atomic mass will give you the number of grams in every mole of hydrogen gas. Cool. Go back up to our work. Let's finish this problem out. Okay, so for every 1 mole, 1 mole of hydrogen gas, 1 mole of H2, will weigh 2.0158 grams. This is the molar mass. That's supposed to be an O. Molar mass. Terrible handwriting, sorry. Okay, moles H2 cancel out moles H2. We're left with the units we need. Grams of hydrogen, H2. Cool, get the calculator out. One way to do this is to take 12 times 2.0158, put that answer in your calculator, divide it by 2. Another way is to take 12 divided by 2, which is 6. Multiply 6 times 2.0158, and you're going to get 12 point something. It is 12.095. Well, the calculator is actually going to be 12.0948 grams. Put that in parentheses. How many sig figs do we have here? Well, we got 12, but I consider that an exact number. We know we have exactly 12 moles. Someone else might say, no, that's only 2 sig figs because it could have been 12.0. Your call. Ask your teacher for some direction. I definitely think this is an exact number. It takes exactly 1 mole of H2 to produce 2 moles of HI. So these are exact. Don't use exact numbers when figuring out the number of significant figures. This number's got 5 significant figures. So that's, you don't want to use 6 here. So you can decide, are there 2 significant figures? I'm leaning towards no. I think there's 5 significant figures. So that's when I rounded it to 12.095. Okay. Here we go. So we've been leading up to this. Here's the main thing. Here is a real stoichiometry problem. If you're in the lab or you're working for a chemical company and some orders, hey, I want to buy 250 grams of hydroiodic acid to do a chemistry experiment. Make it for me. Well, the boss says, well, go figure out how to do that in the lab. How many grams of hydrogen gas are you going to need to produce 250 grams of hydroiodic acid, right? So what we do, well, dimensional analysis. It's, what do we want? We want grams of hydrogen. So over here, I'll put grams of hydrogen, H2, equals, and then a big line off the side here. Scan the question for some numbers. There they are, it's 250. That's what I know, or what I'm given, of which molecule, HI. Step 3 is find conversion factors. Well, I don't have to change the grams, it looks like. We start with grams, end with grams. Cool. Halfway there. Ooh, but the molecules don't match. HI needs to be converted into H2. And the only way to convert molecules into molecules is using the balance equation. What are the units up here? The units are moles for the balance equation. Balance equation says you can, if you have 1 mole of H2, you're going to make 2 moles of HI. So to change HI into H2, you have to go through moles. So that's the first step. Get out of grams. So we need to cancel out the grams and get into moles of HI. Moles over gram is the conversion factor. Hey, that kind of looks like grams per mole. That's the unit of molar mass. It is molar mass, but upside down. We're dividing by the molar mass. What's the molar mass of HI? We actually calculated that, didn't we? Let's look around until we find it. There it is. 1 mole of HI weighs, well, go to the periodic table, grab the weight of hydrogen, 1.0079, grab the mole of iodide, 126.9045, add them together, And there is the molar mass of HI, 127.9124. Yeah, that's the question we're going to do in a minute. Okay, so 1 mole of HI, add up the mass of those atoms, 1 hydrogen, 1 iodide, and the weight is 127. Okay, squeeze it in here. 127.9124 grams. And that cancels out the grams of HI, converts it to moles. Nice. But we want hydrogen gas, not HI. So get out of moles of HI and into moles of H2. How do we convert one molecule into another molecule? Through the balance equation. So right here, we're using the balanced equation. The recipe says there's a 2 in front of HI. The HI is on the bottom. So put the 2 next to the HI here because there's a 2 in the balanced chemical equation. In front of the H2, there's a 1. Yep, 1 mole of hydrogen gas will produce 2 moles of HI. But we want grams. So cancel out the moles of HI. Cool. Now we have to cancel out the moles of H2 and convert them to grams of H2. That's the molar mass again. It's of hydrogen gas. The other molar mass is of hydroiodic acid. And then what was that number? 2.0 something? Yeah, because we just did it right up here. There it is. It's 2.0158. 2.0158. That's how many grams are in 1 mole, Avogadro's number of hydrogen gas. Cool. If time is called on my exam, you turn this in with no number here, you're going to get all the points except for 1. That's all that's left. Just put this number in your calculator. That's not chemistry, that's mathematics. You already showed me all the chemistry calculations over here. So what do? In your calculator, you take 250 times 1 times 1 times 2.058. I did that off the side here. It is it this one? It is 503.95 divided by, well, 127.9124 times 2 times a 1. Yeah, times 1 is it itself, right? So that is 255. 127.9 something times 2 is 255.8248. And then divide these two numbers. And how many significant figures should we keep? Well, this 0 is ambiguous, right? So 0 is after the decimal place, like this one, we count as a sig fig. If you have zeros before the decimal place, there's no other numbers in front of it, you don't count them, but between a digit and a decimal place, the 0, it's not certain whether we count this or not. So it's your call. We're either going to have 2 sig figs or 3. I'm going to choose 3. I'll err on the safer side. 3 sig figs here. We're dividing by 7, and these are exact numbers. That 1's exact. 1 mole of HI, exactly 1 mole, weighs 127.9124. Same here. So I'm thinking, let's keep 3 significant figures. That's the calculation, the number with the fewest significant figures. So dividing these and keeping 3 sig figs, I got 1.97. There we go. And that's a little stoichiometry. I got this balance here, this scale in the grocery store. Someone's weighing a bunch of apples. So I just want to make this one analogy here. In the lab, if you were working for the chemical company and you're trying to fulfill this order of 250 grams of HI, in the lab, you need to weigh out 1.97 grams of hydrogen. So you put it on a balance, keep adding more and more hydrogen like you would add apples. Watch the weight go up, and once the weight hits 1.97 grams, you know you have the right number of moles for the recipe to make 250 grams of HI. That's what these calculations are doing for you. By weighing it, effectively, we're counting out how many molecules there are, and we got it in the right ratio. For every one of these, we get 2 of those, and then we got the weight of each of those molecules tied in here too. It's kind of cool. That's stoichiometry, converting from grams to moles so we can use the balance equation, and then back to grams again so we can weigh them out in the real world. Let's end with this problem. Okay, so I was thinking, let's just kind of challenge ourselves here. I don't think this exact wording would be on the exam. There's a lot going on here, but I just want to tie in some stuff from previous videos as a review as we introduce this new topic of calculations of chemical reactions, stoichiometry. So here's the question. How many grams of NaOH, sodium hydroxide, are required to react with FeCH3CO2? What the heck is this? It's a polyatomic ion we need to memorize. That's acetate, and there's 2 acetates. If we go to the periodic table, we can look up Fe. You don't have to memorize that. Chemical periodic table's right here. Here's Fe, and it's iron. If you can read that font size, it's iron. So this is iron acetate. Iron's a transition metal, so we really should identify its charge. So acetate, again, you have to know your polyatomic ions to know this. Acetate has a -1 charge, and there's 2 of them. There's only one Fe, and nature says this makes a stable molecule because the charges are balanced. How can that be? Well, if each acetate has a -1, iron must balance all the negative charge by having a +2. There we go. This is iron 2, Roman numeral 2 acetate. And we want to react these 2 molecules to produce 6.75 grams of iron 2 hydroxide. Well, iron 2, remember the Roman numeral, tells us the charge on the iron. Hydroxide is OH. And then we have to memorize what's its charge? -1. So the balance, the charges, we need 2 hydroxide ions. So the chemical formula of iron 2 hydroxide is FeOH in parentheses 2 outside the parentheses. Okay, I hope that helped break down the question. In the lab, you need to measure out so many grams of this so you can produce this many grams of iron 2 hydroxide. How do we do this? Dimensional analysis. Okay, so what do we want? 1 grams of NaOH. Put that over here. Grams of NaOH equals, and then a big line. That's step 1. Step 2, find some digits. 6.75. What are the units? Grams. Of which molecule? I count that as a unit. Iron 2 hydroxide. I'm going to use the chemical formula. If you wanted to write the words here, you could do that too. You could write the name of the compound there. Step 3, find conversion factors such that we change grams to grams. Wait. No, more importantly, we have to change this molecule, FeO2, OH2, into NaOH. How do we change molecules to molecules? Balance equation. Where's the balance equation? We got to figure one out. Yeah, so this is where the review comes in. Okay, so what is the recipe here? Let's figure it out. Well, 1 ingredient, 1 reactant is NaOH. It says how many grams of NaOH are required to react with iron acetate. That's a second reagent. And we're going to produce, that's what it says, to produce 6.75 grams of iron hydroxide. Cool. Wait, we need it balanced. So I see some Na on this side. Where's the Na on that side? There's another molecule here being made. And we have to figure out what that is. Remember when we were doing net ionic equations and complete ionic equations and all that stuff? So we've worked on this problem before. A good strategy for predicting products is to switch the cations. Let's try that here. So let's predict the products. So what we want to do is identify the cations. They're usually listed first in their chemical formula. Na and OH are the two pieces, the two ions here. If you don't know the charge on sodium, Na, or if you don't know Na stands for sodium, go look it up. You get the periodic table on all my exams. Na is element 11, and there's the word sodium underneath it. More importantly, it's in column 1A. That little 1 identifies the valence electrons. Yeah, sodium has 1 valence electron. And this is an ionic molecule. It's got a metal, sodium, with OHs. Oxygen, hydrogen are nonmetals. Metals stick to nonmetals by ionic bonding, and metals tend to lose electrons. Yeah, sodium has a 1 valence electron, wants to kick it out, become positive. Another way to think about it is 11 electrons that sodium has. It would prefer to have 10 like neons, so it wants to lose 1. So we predict that sodium has a +1 charge. We need to memorize our polyatomic ions. Hydroxide has a -1 charge, and hey, that matches. That makes a stable molecule. Excellent. We already found the components of iron acetate. The cation is Fe2+. The anion is acetate. Okay, and some of you are saying, wait, Dennis, there's 2 acetates. And that's true, there are. But if I don't put 2 acetates here when I'm trying to figure out the products, I need to know there's 2 acetates when I balance it. And that's a separate step. So I don't like the mix of steps. It gets to be confusing. So just list 1 cation, 1 anion, even if there's more than 1. And then switch the cations. Meaning that, hey, sodium, leave hydroxide and go pair up with acetate. And iron, you go hang out with hydroxide. And it turns out the problem told us what the first product was. It's iron hydroxide. And I hope that makes sense. When iron 2+ tries to group up with hydroxide ion, nature says you need to balance the charges. You need another hydroxide ion. So you have a net -2 balancing the +2. And that's the correct formula. Sodium, you're pairing up with acetate. Hey, the charges balance. So one of each will make a stable molecule, sodium acetate. Good, we're done. We're done predicting products, but we're after the balance equation. All right, balance equation. 2 things to remember. Don't change your subscripts. That 3, that 2, can't touch those, leave them alone. And save the simplest for last. So these molecules that have parentheses are not simple looking, so that's not my simplest molecule. This one is, right? This only has 3 elements in it, sodium, oxygen, hydrogen. This one has 4, a sodium, a carbon, a hydrogen, and an oxygen. That's more complicated. So I think of the sodium hydroxide as the simplest molecule. So my tip is, don't balance this one first. Work on other elements. Don't balance sodium, don't balance oxygen, don't balance hydrogen. Go after iron or carbon. So I don't know, either one works. Let's pick iron. Hey, there's 1 iron on the left side, and there's also 1 iron on the right. Excellent. They're already balanced. Iron's balanced. Carbon, you're next. Let's see. Inside the parentheses, I see 2 C's, but outside there's a 2. That's a total of 4 carbons. None carbons over there. There are 4 carbons on the left-hand side, and on the right, there's only 2. I need twice as many more. So we're going to put a 2 here. So we have 4 carbons altogether. Now it's time to balance sodium, oxygen, hydrogen. So I'm gonna go after sodium first. There's 1 on the left, but now there's 2 on the right. So I need a 2 here. How about the oxygens? Well, there's 2 oxygens in the 2 sodium hydroxides. There's 2 O's in here, times 2 is 4. So there's 4 oxygens in this molecule, 2 more here, a total of 6. 6 oxygens on the left. Over here, there's 2 O's. And in the molecule, there's 2 times 2, there's 4 oxygens here. And on the right side, there's a total of 6. Hey, that's balance. Nice. Hydrogen, how you guys doing? There's 2 H's. And then here there's 3 times 2, there's 6 more. 2 plus 6 is 8 H's. And then here's 2. And then 3 times 2, 6 again. Yeah, 2 plus 6 is also 8. Hydrogen's balanced. We have a balanced equation. 2 sodium hydroxides will make 1 iron hydroxide. Perfect. Okay, now we can move on. We know how to convert moles of iron hydroxide to moles of sodium hydroxide. The ratio is every 2 moles will produce 1 mole of iron hydroxide. But to use this conversion factor, we need to get the units of moles. So get out of grams of this molecule and change them into moles of iron hydroxide. Grams, moles, that's molar mass. And that's going to equal, okay, squeeze it in here, the mass of iron. This is going to get messy. Let's slide down. So go down here. Well, we can at least pencil in 2 oxygens and 2 H's, right? Those are all the atoms in the formula. So the molar mass of iron hydroxide, iron 2 hydroxide, is the weight of 1 iron, the weight of 2 oxygen atoms, and the weight of 2 hydrogens. Go to the periodic table. Iron weighs 55.847. Hydrogen is 1.0079. Oxygen is 15.9994. Grab those numbers, add them all up. So if you like the math, you can stick around for that. Otherwise, you can fast forward the video because I misplaced those numbers. There they are. 55.847. And then 2 times 15.9994 and 2 times 1.0079. Add that all up and I get 89.8616 grams per mole. 89.8616. All right. So every 1 mole of iron hydroxide will weigh 89.8616 grams. That's molar mass. Cool. That takes care of the grams of iron hydroxide. They cancel out. But we've still got more work to do. We're in moles of iron, so we can change the molecules now. So get out of moles of iron hydroxide and change them into moles of sodium hydroxide. Get out of this molecule and into the other one. What's our conversion factor? It's the coefficients in our balance equation. So in front of the iron hydroxide, there's an invisible 1. And in front of the sodium hydroxide, there's a 2. Yeah, because you need 2 moles of sodium hydroxide to make 1 mole of product. And we're almost done. We got the right molecule, sodium hydroxide. We just need to cancel moles and get into grams. So cancel out the moles and get into grams of sodium hydroxide. This is molar mass again. Need the mass of a sodium, an oxygen, and a hydrogen, because those are the atoms in sodium hydroxide, and that's 22.9898. Oxygen's 15.9994. Hydrogen is 0.749. The whole thing adds up to 39, sorry. 39.9971 for every 1 mole. And I got all the credits so far. If that was your work on an exam question, almost done. If you run out of time, you missed a point because you didn't put in the numbers into your calculator. So let's do that and get that last point. 6.75 times 1 times 2 times 39.9971. That's a big number. I'll put it over here. I got 539.96085, all divided by 89.8616 times 1 times 1. Oh, well, that's easy. I can do that in my head. I like multiplying by 1. That's easy. And then finally, in your calculator, take this top number, divide it by the bottom, get a big number, and then how many significant figures should we carry? Well, there's 3 here. That's an exact number. There's 6 sig figs, so 3 wins. These are exact. Well, there's 6 sig figs there, so still 3. Yeah, and that's the exact number. So we're going to carry 3 significant figures. So divide that, round off the 3 sig figs, and it's 6.01 grams of sodium hydroxide. All right. I hope this is helpful. I'll see you in the next video.